Let's jump right into the Causal Memory Gravity or CMG research program. We're going to keep things precise, restrained, and strictly academic today as we trace this framework's boundaries, stepping from its microscopic Planck scale roots all the way up to its macroscopic cosmological benchmarks. We'll map this out in 6 parts, starting with the CMG framework and its mathematical formalism, then diving into the microscopic origin. After that, we'll look at linear observables, review its current cosmological status, and finally, outline the open questions. Section 1. The CMG framework, space-time memory. What does it actually mean for space-time to have memory? Well, we are not claiming to instantaneously answer the big open problems in cosmology here. Instead, CMG explores a very specific hypothesis. What if space-time doesn't instantly forget its past curvature? In standard general relativity, gravity responds to matter right here, right now. But in CMG, we introduce a delayed gravitational response. It's sourced by a retarded nonlocal kernel. This basically means gravity acts with a built-in time delay based on causality, so it responds not just to present matter, but to the causal past of curvature. Moving to Section 2, Mathematical Formalism, the effective action. So, how is this memory actually encoded mathematically? If you look at the core effective action, you'll spot the standard Einstein-Hilbert baseline, but it's modified by this non-local curvature memory term containing a retarded inverse operator. This is what formally enforces that gravity remembers the causal past. It introduces a single-dimensionless coupling, eta, which is defined as negative alpha tilde, alongside a memory relaxation scale, beta. Now, for practical calculations, this can also be mapped to an equivalent local auxiliary field, U, where the D'Alembert operator plus beta squared acting on U equals negative R. Of course, anytime you modify gravity, you absolutely have to verify stability. And there is a rigorous classical stability window here. The dimensionless coupling alpha tilde must sit strictly between -1 and 0, which means eta sits between 0 and 1. As long as you stay within those specific bounds, the framework is conditionally stable. The linear scalar mode yields no ghost or tachyon modes at the tree level, meaning the theory remains physically viable. Section 3. Microscopic origin, the dynamic Planck network. We have the continuum field theory, but what is the actual microscopic substrate creating this memory? The proposal here is the dynamic Planck network, or DPN. Instead of a perfectly smooth continuum, imagine spacetime at the Planck scale as a discrete causal graph, a locally finite web of cells carrying tutorial degrees of freedom. And here's the really elegant part. Through coarse graining, that macroscopic memory scale beta we just looked at is directly determined by the spectral gap of the network's graph Laplacian. The memory isn't an arbitrary add-on. It literally emerges from the discrete network's relaxation rate. This provides us with a beautifully structured scale span. We step up sequentially, starting from the fundamental Planck scale network at the base, moving up to quasi-static galactic dynamics where we test the halo response, and finally reaching late-time linear cosmology. Which brings us to Section 4, Linear Observables, the Poisson modifier. Stepping up to those cosmological scales, we need to know exactly how CMG modifies observable structure growth. At the linear perturbation level, it introduces a scale-dependent Poisson modifier, mu. Assuming a no-slip benchmark where gamma equals 1, this specific equation smoothly weakens gravity on large scales. If you were looking at very small spatial scales, meaning a high wave number k, mu just approaches 1, giving us standard general relativity. But on massive cosmic scales, mu drops toward 1 minus eta. That transition is entirely controlled by the inverse length memory scale, beta. To maintain consistency, we need clear mathematical pathways back to established physics. And we have 2 distinct perturbative limits here. General relativity is perfectly recovered if we either take the memory amplitude eta to 0, meaning the memory effect vanishes completely, or we take the inverse length scale beta to 0. In both of these limits, the framework safely collapses back to standard Einsteinian predictions. Next is Section 5, Cosmological Status, DSI DR1 Benchmark. Let's ground this theory in empirical reality using robust full-shape clustering data. What you're seeing is a direct comparison of the CMG linear sector against the DESI DR1 6-tracer shape-fit vector. This serves as our covariance-aware linear benchmark, plotting the compressed growth observable, F sigma 8, across various redshifts. And notice how closely the solid line of the CMG fit hugs the dashed exact growth GR template. In fact, when we calculate the full covariance likelihood, the compressed amplitude fit, AG, sits essentially right at 1, 0.9962 to be exact. This near-GR benchmark proves that while linear CMG is perfectly allowed statistically by the data, it is absolutely not preferred over standard lambda CDM. The deviation from general relativity here is statistically null. It is critical to state explicitly, the linear CMG sector alone does not resolve our current cosmological tensions. Finally, Section 6, Open Questions, Boundaries of the Program. To maintain epistemic discipline, we have to acknowledge what remains unproven. Achieving full CMB compatibility and completing the DPN cross-scale calibration are both deferred to future work. Also, any hope of assessing or resolving cosmological tensions like S8 relies entirely on a nonlinear screening mechanism. Right now, that mechanism is treated purely as an uncalibrated effective field theory closure ansatz. The linear benchmark we just analyzed does not validate that nonlinear screened sector. So I'll leave you with this falsifiable question to define the precise boundary of our current knowledge. Can upcoming nonlinear structure surveys successfully calibrate and rigorously falsify the EFT closure ansatz for CMG screening? If spacetime truly does possess causal memory, it is within the complex, dense environments of nonlinear cosmic structures that this theory will face its ultimate reckoning. Thank you for joining me to unpack this fascinating research program.